All right, so we're starting chapter 2.5, Fundamental Theorem of Algebra. We're going to begin with a little warm-up, reminding us how to do some operations with complex numbers. So I'm going to go ahead and jump into this. So we have here first complex number. Remember, complex numbers are always written of the form a plus bi, where a is the real part, b is the imaginary part. Either of these could be 0. So if the real part was 0, then we'd be dealing with a purely imaginary number, something I. And if the imaginary part was 0, we'd be dealing with something that's purely just a real number. All right, so we have 3 minus 5i, and we're subtracting this complex number, 2 plus 7i. I like to think about this similar to like terms. I'm only putting together the real parts with the real parts, imaginary parts with the imaginary parts. So here I have 3 minus 2. So the real part's going to be 1. And then for the imaginary part, I have negative 5i minus 7i. That's going to be negative 12i. And so that would be our answer there for that subtraction. Here, we're multiplying two complex numbers together. We can do this however we want. I'm just going to distribute. So I'm multiplying the real part times the real part times this imaginary part. I'm going to do the same thing here. Whatever you want to call this, FOIL, double distributing, or you could even use an area model like a generic rectangle to multiply this out. All right, so we have 1 times 4, 1 times 2i, negative I times 4, negative 4i, and then negative I times 2i, that's going to be negative 2i squared. Now, I squared is, remember, real quick, I is the square root of negative 1. So then I squared is going to be taking that and squaring it. Obviously, that cancels out the square root, so we end up with just negative 1. So anytime we have I squared, we're just going to be replacing that with negative 1. So let's go ahead and show that work. So this is negative 2 times negative 1. Really, that becomes plus 2, right? You kind of ignore all that stuff. All right, simplifying this, I have 4 plus 2 is 6. 2i minus 4i will be negative 2i. So there we go. That's the answer of this multiplication. Okay, and then we have another one involving some radicals. This one, I will just give fair warning, is going to be pretty messy to multiply out. So I'm going to, trying to just move this answer. Move that answer up here so that I can just erase this stuff. Give myself some space to do the problem. All right, same idea. We are multiplying these together. So root 2 times root 6 is going to be square root 12. Square root 2 times I is going to be root 2i. Negative 3i times root 6 is going to be negative 3i root 6. And negative 3i times I will be negative 3i squared. Remember, that's just going to be a negative 1. So that'll become plus 3. Square root of 12 is 2 root 3 when we simplify this, because 12 is really 4 times 3. So we can take the square root of 4 there. These are not going to go together nicely just because we don't have a lot of the same radicals. I'm going to write these in a consistent way. You can put the I after the number, or some people like to tuck it in here so that it's not confused as being inside the radical. That's just something people do. All right, so our real parts are going to be here and here. So 2 root 3 plus 3, that's going to be our real part. And now our imaginary part, a little trickier. I have root 2, and I have minus 3 root 6. So that's going to be root 2 minus 3 root 6. That's our imaginary part. Goes with the I. Very, very messy number. Complex number, this being our real part, this being our imaginary part. This is the exact answer. Again, pretty messy. We won't be doing a lot with stuff that messy. Okay, let's go ahead and clear that and just review a little bit more about complex numbers. Okay, so complex numbers. The complex numbers are a kind of bigger group of numbers, so to speak. So if you think about all the numbers that we could possibly have here, complex numbers is sort of like the biggest set of them. It includes everything. Some of those numbers are real numbers. So like a smaller grouping of those are real numbers. Those are the ones where we have just a real part and our imaginary part is 0. So those would be the reals. And then another smaller group of those would be the purely imaginary numbers. So let's just write a couple examples of some numbers that would fit in these categories real quick. So a purely real number would be like 3 or pi or square, or sorry, purely real numbers. These are our reals. So the square root of 2, right? These are all purely real numbers. There's no imaginary part to it. The imaginary numbers would be something like 3i or the square root of -10. Obviously, that would involve I as our answer in there. And then complex numbers, those are all that are going to have both a real part and an imaginary part. So something that's a plus bi, that's going to be our complex numbers. So it's kind of a set diagram of these particular values. When we're dealing with the solutions to polynomials, so far we've talked about how to come up with real solutions. In Algebra 2, you discussed how to come up with these other ones, and that's what we're going to really be delving into is what happens if our solutions are not real numbers? What if they happen to be either a purely imaginary number or a complex number? So we're going to get into that. We also need to remember what's going on with I. So I is the imaginary number. So just kind of quick review here. Let's say we're taking the square root of -20. Remember, what we do here is we pretend that this is the square root of 20, and we just have to kind of factor out that square root of -1. And we define the square root of -1 as the imaginary number I. So whatever we get with this, we're going to tack an I onto it, and that's how we simplify negative radicals. Obviously, this is 4 times 5, so square root of 4 is 2. We get 2 root 5i. This is a good point of why sometimes we write this a little differently, because the way I drew that line makes it appear a little misleading as though the I was underneath there. So a lot of times you will see people write answers like this. Just so that it's clear the I is not underneath the radical. Either one is fine, just be careful to not put that radical extending over your I. Okay, powers of I. A lot of times we're going to be raising I to a certain power, either to the first power or the second power or third power. We're probably not going to go much higher than that, though we could if we really wanted to. I has a pretty interesting property. It's going to cycle through these 4 values. So like I to the first is going to be just I. I squared, which you just talked about before, is -1. I to the third is going to be -I. I to the fourth is 1. That's a really useful one. And then we go back up here, and I to the fifth is going to be the same thing as just I. We can kind of take a look at that, what's going on here. So we've already talked about I squared, how we're just squaring the square root of -1, thus we end up with just -1. We can kind of make use of that. If we know I squared is -1, we can kind of use some exponent rules to help us figure out some of these higher powers. So I to the third can be written as I squared times I to the first, right? 2 plus 1 is 3, so that's equivalent. We just saw how I squared was -1, and I to the first is just I. If you multiply -1 times I, you end up with just -I. That's great. We reduce the power of it, it's a little easier to work with. And I to the fourth is even nicer, because I to the fourth can be written as I squared times I squared, which is -1 times -1, or +1. That's a very useful one when we're dealing with higher powers. So just kind of briefly look here, I to the fifth can be written as I to the fourth times I to the first. We know I to the fourth from just before is 1, so this is 1 times I. That's where we get just I. And this kind of keeps going here. I to the sixth being I to the fourth times I to the second. 1 times -1, which is just -1. And we're kind of repeating that cycle over and over again. Again, mostly we're going to be dealing with i's in this power range, but we could do something even kind of absurd like I to the 30th if we wanted to. Well, the way we would do something like this is we'd see, all right, well, I know I to the fourth is 1, so how many I to the fourths do I need to make that up? 30 divided by 4 is going to be 7.5. So it can go in there 7 times whole. So I to the fourth to the 7th. Remember, this is just 1 to the 7th, which is 1, times, that's 28. So we need 2 more i's, so times I squared. And we know that that's actually just -1. So 1 to the 7th is just 1 times -1. So then this thing is just equal to -1. And you can do that with any power of I you really want to. We won't really be doing that so much. We mostly be dealing with these lower powers of I, but it's worth knowing. All right. I'm going to go ahead and stop this video here and